So with this question, we've been asked to prove that the vertices of the triangle form a isosceles triangle. So obviously an isosceles triangle, we've got two sides that are the same and one that's different. So we've got to prove that here. Okay, so we could sort of graph these points and see, whether it looks like it's isosceles to start with, and that might help us sort of prove it. But best way to do it is just to find the distance between each of the points and then work out that you've got two the same and one different. So let's have a look. We've got the distance of AB. So our distance formula, hopefully you remember, is the square root of x2 minus x1 all squared plus y2 minus y1 all squared, where we might label them x1, y1, x2, y2. Because we've got three coordinates here, you could really say x3, y3. But basically, we're going to start off by trying to find the distance between A and B. So AB with a little line above it to say it's a distance. So let's just substitute in here. We're going to have x2, so x2 is 2, minus x1, which is negative 3, all squared, plus y2, which is 13, minus y1, which is 5, all squared. Let's go through. We could at that stage put it on the calculator, but we really should get good at doing these without a calculator, because in math methods you won't be able to use a calculator. So let's have a look. We're going to have a positive here, so it's going to be 5 squared, which is 25, plus we're going to have 8 squared there, which is 64. So we're going to have the square root of 89 units here, and we're going to leave it as an exact value, simply because we don't need to know what the square root of 89 is. What we're looking for is another side that has the same distance as that. So let's try now with AC, distance for AC. Now, it's our formula, gets written out again. Well, we don't need to write out the formula, but what we might do is now change it so that we've got this being x2, y2 over here. So our x2 that we're going to start with is 5 minus x1, which is negative 3 again, so negative 3 getting squared, plus y2, which is 0, minus y1, which is 5, it's getting squared as well. Then we have a look and we go, okay, well, we've got it's being a plus, so that's going to be 8 squared, 64, plus, now we've got negative 5 in this bracket, but negative 5 all squared gives positive 25. So again, we get the square root of 89 units. Again, like you could get out your calculator and say, well, it's 9 point something, but you don't really need to do that for this. So what we've got here is that AB is equal to AC. We've almost proved that it's an isosceles triangle, but the problem is here, if the last side, if BC is equal to 89 units, we don't have an isosceles triangle. We've actually got an equilateral triangle where all three sides are equal. So unfortunately, we do need to use the distance formula again. So I'd probably go underneath here normally, but I'm just going to go over to the side here and say we've got BC. BC will be the square root. Now let's just change this now. So this is x1 and that's y1. And we're going to say, okay, it's x2, which is 5, minus x1, which is 2, getting squared, plus we're going to have y2, which is 0, minus y1, which is 13. It's getting squared as well. And we're going to have then 3 squared, which is 9, plus negative 13 getting squared. Well, it's the same as 13 squared, which is 169. And so we've got the square root of 178 for that units. So because that's different, and we might even say, therefore, triangle ABC is isosceles as AB is equal to AC, but it's not equal to BC. Or simply that you've got two sides of the same length and one that's different.